Welcome. The title of today's notes worksheet is Parabolas Day 1. We will initially be exploring some of the geometric characteristics of parabolas, and that's what the top of your page suggests there. So we're going to need a ruler to go ahead and do a couple of measurements with the parabola that I've provided for you. And then what we'll probably do is transition into the more the interplay between that geometry and the algebra on the coordinate plane. So why don't we go ahead and get started here. It looks like I've pasted a little picture of the parabola, and so let's go ahead and do a quick explanation. So here, everybody, that the plane is going to intersect the cone in a very particular way. It's going to come in, as a matter of fact, parallel to one side of the cone. So does everyone see the side of the cone right here? So now our plane is going to intersect our cone parallel to that. So it comes in kind of like this right here. And when it does, I get actually our first open curve. So there's our parabola right there. At this point in time, we've explored circles and ellipses, which are called closed curves. And this parabola right here, as you can see, is an open curve. These branches, these arms of the parabola, extend to infinity. So we'll go ahead and take a look at that piece. Obviously, what we want to do is go ahead and get you a definition of this. And we'll do it a very similar approach to the way I did ellipses. We're going to do it in what I would call a static perspective, meaning just one parabola right here and seeing if we can come up with a couple measurements. But then hopefully I'll be able to show it to you from a more dynamic perspective using my program. So why don't we go ahead and get started? You're going to go ahead and need a ruler to pull this off. And what we're going to do is pick a point on the parabola, if you would, anywhere you'd like. Go ahead and pick a point. And what I want you to do is actually measure the distance right to this point inside the parabola, which is called the focus. So if everyone can go ahead and do that piece right there, you're going to measure the distance from the focus to the point on the parabola. And again, go metric if you would, just more tick marks there. And then please go ahead and just put your answer right there if you would. Okay, so you're going to have that piece, that number, whatever it may be. Have no idea what it is. Yours is obviously going to differ from mine. Yours is on a paper, mine's on the board. So you're just going to have to go ahead and fill in your particular number. All right, now everybody, here's the idea. This was what's going to get a touch tricky, and I don't need you to be totally precise, but try to do the best you can. So what I'm going to ask you to do now is find the distance from the point on the parabola to this line that is running right behind it. Does everyone see this? This is what's called the directrix. And the directrix is a line that is perpendicular to that axis of symmetry. You don't have to draw the axis of symmetry there. But if you remember axis of symmetry from Algebra 1 and Algebra 2, kind of divides the parabola into two equivalent parts there, two symmetrical parts. Well, this directrix is perpendicular to it, and it runs behind the vertex. So if you remember, that's the vertex right there. Well, what I'm going to ask you to do is find the distance from that point to the directrix. Now, when we talk about a distance from a point to a line, we have to be a little careful. The direct distance is coming at it perfectly perpendicular, so it should look something like that. So again, just do the best you can. Obviously, we don't want to do the distance all the way over here or all the way over here or something. I want the direct distance. So the shortest distance possible comes in perpendicular. So see what you can do. And again, from your point to that line, please. And put your number right there. And just kind of hold off on a conclusion for a moment. We'll probably do it just one or two more times there just to solidify a couple ideas. Okay, so the hope is at this point you've measured the distance from the focus to our point on the parabola and from the directrix to that same point on the parabola. And maybe you notice something about those two values. All right, let's go ahead and continue. Secondary point, anywhere you'd like, your call. And if you would, same exact situation. Repeat the process if you would. Please measure the distance between your point and the focus. And when you do that, everybody, that has to go right there if you would. And then what I'll ask you to do, of course, is measure the distance between your point and the directrix. And again, going in, just try to go as perpendicular as possible. I won't make you construct it out there to ensure it's perpendicular. Just do the best you can. All right, so we've got two distances from here to here and there to there, and that's what I'm looking for, of course. So you put your numbers in if you would. That would be great. I'll ask you to do it just one more time if you can. If you need to pause me for a moment to do your measurements, that's great. If you are ready to roll, let's do it. So I'm going to pick one more point. Again, anywhere. It doesn't matter, guys. Anywhere you'd like. You don't have to pick the points that I pick. But basically, find a point on the parabola and grab your ruler and go right to the focus, if you would. Just like that. And measure that length of segment or the distance between those 2 points, and it's going to be something, whatever it may be. And then repeat that process going right to the directrix. If you can, right on down there. That's looking pretty nice, if I do say so myself. And so try to go in perpendicular if you can, as best as possible, and measure the distance between our point and the directrix. And that looks great. Obviously, guys, I can continue. I can do this again and again and again. But I'm hoping you see sort of the pattern here. These distances should be the same. So from any arbitrary point on the parabola, the distance to the focus is the same as the distance to the directrix. So if I was to maybe have sort of highlight this a little bit in our diagram here, let's throw some tick marks on that. That segment would be congruent to that segment right there. Theoretically, and again, you probably did this a little better than I did up there, but those 2 segments would be congruent. And this one right here is the same as this one right here, so you can kind of see that piece. The infinite number of points on the parabola are equidistant to the focus and to the directrix. And that's pretty much going to be our definition. What do you say we throw that in place? I'm going to go ahead and just quickly get rid of that piece so it doesn't get in our way. But let's get our third definition that you are responsible for. And remember, all of them start out the same. So here we go. Set of all points in a plane. Came up with a couple good definitions for circles and ellipses. Let's do parabolas. So set of all points in a plane, and this is where it diverges. So here we go. That are equidistant, and that's what we saw right there with those tick marks. So equidistant from a given point and that given point, everybody, is going to be called the focus. And in this case, a given line. And that given line is what is called the directrix. And that looks really quite outstanding. Very, very cool. Okay, so we kind of did that with our parabola that I gave you there. I'm hoping you saw those results as best as possible. If it's not perfect, don't worry about it too much there. Let me go ahead and bring up my Sketchpad program, and I've got it kind of ready here. And you can kind of see the definition that we just came up with. And we're going to have this piece right here. So everyone, here's your focus. Here's your directrix. Just, drop the pencil for a second and just peek. And I'm going to do the same. Here are the distances, guys, from point to focus and from point to directrix. And let's go ahead and I'm going to collect. When it says locus, what that basically means is you're collecting all of the points in the plane. And there we go. So all of the points equidistant to the focus and the directrix there. And you can see that nice parabolic shape form. I'm going to actually go ahead and hit Show Parabola right over here so you can really see it. And there it is. It's collecting all those points. Obviously, it's stopping at some point in time just so it can go back and forth. But essentially, they would follow the parabolic line to infinity. Pretty cool, huh? Nice. Let's see. Well, let's stop that, and let's get right on back to it. Okay, so this first part is completed. Let's see if there's anything else we need to add at this point. No, I think it's time to go ahead and make that transition. Now what we're going to do, of course, is throw this thing on the coordinate plane. Let's go ahead and see the interplay between the geometry and the algebra. So first order of business, day one usually starts out relatively easy with the algebra. And so in this case, everybody, it says modeling a parabola on the coordinate plane. And here's the key if you can box this up. So we're going to start this out vertex at the origin. So vertex at the origin. Should know what the vertex of a parabola looks like. And what we're going to do is really see four different parabolas form here. So we're going to see two opening horizontally and 2 opening vertically. So why don't we just go ahead and sketch that out just for good measure here. And so kind of that U-shaped curve, kind of like this. We're going to see parabolas opening to the left. We're going to see parabolas opening to the right, and these aren't great drawings, but you'll get the gist of it. Oops. So let's get that. There we go. So we could see one opening to the left, one opening to the right. We're going to see a couple vertical in nature. So you've seen these before because these are functions, but one opening up. And another one, how about opening down, something like that. So those are the 4 directions that we're going to see the parabolas open. We're not going to see any diagonals or anything like that. This is what we're limited to for this particular section. So this looks great. Notice again, just one quick connection to our curriculum so far. We've seen these 2 parabolas before. I think I quickly alluded to it because these are functions, right? These pass the vertical line test. So we've explored these on the coordinate plane. We haven't looked at these on the coordinate plane because when we did quadratic functions basically. And these do not pass the vertical line test, and so they're not functions. But regardless, they are quadratic in nature. They're what are called quadratic relations. So they are a representation of 2 variable quantities, just don't fit the characteristics of being a function. Okay, enough rambling. Let's go to it. So 2 standard forms, of course, that we're going to see. So let's go ahead and highlight a couple pieces right here. Standard form, parabola, vertex at the origin, everybody, opening horizontally. And so in this particular case, the equation is nice and straightforward. The y is actually what's going to be squared here. We're used to seeing the x squared. And we're going to explore this 4px. So we're going to have a constant out in front of our linear term. And in this case, the linear term is the x. So again, not too bad, a pretty easy equation to work with. And then let's go ahead and get the vertical piece. Standard form, of course. We'll transition into general form soon enough. Vertex at the origin, just for now. And in this case, either opening up or opening down, so vertical. And these are the ones we've seen before in a slightly different way, but basically it's going to be the y and the x squared. So x squared equals, and we get this constant in front of the linear term there, and the linear variable is going to be the y. All right, so we'll talk about ways to figure out how to determine which way it opens. We'll do that when we get into some of the examples. All right, a few of the things we've got to fill in here. So characteristics of a horizontal parabola, let's do that piece first. And so if I have a horizontal parabola like this right here, we do want to talk about the directrix, and we do want to talk about where that focus would be and so forth. So the directrix would actually be behind the parabola, perpendicular to the axis of symmetry. So I'm hoping everyone would agree, if I have a parabola opening horizontally, the axis of symmetry is coming through this way, the directrix is actually going to be this. It's going to be vertical. And that's exactly what I need you to write in here. So the directrix is vertical. And I'm going to, of course, ask you to model a vertical line on the coordinate plane. And so you'll have to refresh your memory from way back when. But what do we know about the vertical line on the coordinate plane? Well, what we know is that all of the x coordinates are the same. And so that is how the model is written, essentially. So basically, it's x equals whatever the number is. And again, if you're not sure about that, if that doesn't look too familiar, give it a little time and you'll see this in action. So a vertical line on the coordinate plane, all the x coordinates are the same. And then what we're going to do is talk about this p-value that is embedded in our equations here. So there's our p-value, of course. And if p is positive, greater than 0, of course, then the parabola opens to the right. And I think that would be fairly intuitive. And then if the p-value is negative, it's going to open to the left. So positive right, negative left. Okay, and again, you'll see this backed up with some examples here momentarily. Give it a few if you would. All right, let's go get the vertical one. So the directrix, let's describe that piece. Again, perpendicular to the axis of symmetry. So in this case, the axis of symmetry for a parabola that's vertical would be this. Perpendicular is going to be this, which is horizontal. And that's exactly what I need you to put in right here, if you would. So the directrix is horizontal, absolutely. And how do we model a horizontal line on the coordinate plane? Well, if you remember correctly, it's all the y coordinates are the same. And so just y equals some constant, whatever it may be. I'll just throw a little b in there. I guess I would ask you, what do you think your intuition would tell you, up versus down? Which do you think is which there? So if that p-value is positive, then the parabola is opening up. And if that p-value is negative, then that parabola is opening down. So when I give you an equation, which I probably will in just a few minutes here, the first order of business is to make a determination. Which of the four directions is that parabola opening? Is it left, is it right, is it up, or is it down? All right, now let's get into that p-value. So what you're going to do when you see these models, you're going to see a constant out in front of this variable right here. That constant is equivalent to a factor of 4 greater than p. So that's what this is. It's a 4p. But it's the p-value that sort of affects what we're going to be looking at and the connection to the geometry, basically. So let's get that in place, I guess. So here we go. That p-value is this. It is the distance from the vertex to the focus. And that's really how it is defined, vertex to the focus, both parts of which we were going to explore on the parabolas here. Now secondarily, it's also, and I guess here's how I'm going to do this, I'm going to put a little slash right here. The way the geometry works, it's also the distance from the vertex to the directrix. But I need to clarify that piece. So let's have you write it in first, and then a quick explanation behind it. So distance from the vertex to the directrix, but really in the opposite direction. So that's what I'm going to put right in here. Because the first thing I did on the top line is the true definition. But we also want to use this idea to go ahead and draw some things in. So in opposite direction. So have that in, and then we'll go ahead and take a look at it. So let me go ahead and go back to my screen just for a moment. And everyone, I hope you agree that this is the vertex right here. So if I asked you for the p-value, by definition, the p-value is going to be from the vertex to the focus. So this right here is p. How many units is it from here to here? Now, as you can see, though, that distance happens to be the same as the distance from here to here. Does that sound right to you? Because this is a point on the parabola, and so it is equidistant to the focus and the directrix. But when we talk about p, we really want to talk about it primarily from here to here, because that's where we will really understand direction. But it is also the distance from the vertex to the directrix, just going in the opposite direction. Okay? So if p is positive, and that would be the case right here for a vertical one, it's going up. There we go. That's how I get my focus. But then I would go back down the opposite direction, the same number of units, and start thinking about my directrix. Okay, that might be a touch abstract for you at this point, so it's time to put it together. Here we go. Let's try to utilize this a little bit, see if we can sketch some things out. Again, if I put the infinite number of ordered pairs that make this equation true onto the coordinate plane, it forms a perfect parabola. What I'd like to do is explore the geometry behind that parabola, and that's what we're going to do here. So let's take a look. Let's go for it. First and foremost, letter A. What direction does it open? So we have 4 possibilities. Is it up? Is it down? Is it left? Or is it right? And here's what I do. Just obviously what you're going to do is look on the previous page and try to figure it out from there. But I always look to the right side of the equation. That's where, as long as it's in this nice standard form, I just look to the right side. And here's how I do it. Take it for what it's worth. But this is positive. So the 4p is positive. And the variable that it's sitting next to is an x, which is horizontal. So this is kind of the piece that I have. Positive, horizontal. Well, positive and horizontal means it's opening to the right. So again, I look to this side of the equation right here, and I make my determination from those two things. Positive, and because it's x, I think horizontal, and so it's opening to the right. All right, good. Now what is the value of p? So guys, this, unfortunately, it's not exactly the p-value that we're coveting here. It is a factor of 4 greater than p. And so all you know is just that the 4p is equal to 8. And obviously, notice I kept the numbers pretty simple for you. So what that means is that true distance that we're looking at, vertex to focus in particular, and vertex back to directrix, is not 8 units, it's 2 units. So whatever is right here is equal to a 4 times that p. Good. Well, C and D, let's go get those two. Let's go ahead and utilize our coordinate plane a little bit. I told you today, everyone, we're just going to put the vertex right at the origin. If you could put it there, that would be great. And then P is equivalent to 2. And here's the good news. Once we determined that the parabola is opening to the right, as you saw geometrically, the focus is inside the parabola. And so if the focus is inside the parabola there, it also goes to the right. So whichever way the parabola opens, that's the way we go to the focus. And here, it tells us numerically how many units to go. So nice and straightforward. Everyone just go 2 units to the right. And that's it. P is 2. Direction is right. Pretty straightforward. So I'm going to write a few things down here just to make sure I've got everything covered. But that focus is a point on the coordinate plane. That's the key. And it has an ordered pair, which we just represented, x and y. Now here's the idea. Those two things went hand in hand beautifully to get the focus. I do want the directrix, and so here's the idea. P is 2, and so that told me to go 2 units to the right to put the focus. But we can also use it to get the directrix. We just go in the opposite direction. So I go 2 units back, and I go perpendicular to the way I went back, because this is kind of the axis of symmetry right here. So I go 2 units back, and I draw a perpendicular line to the way I came in. And so everyone, that would be the directrix right there. I hope everyone's in agreement on that piece. Okay, so I drew my directrix. 2 units to the right to get the focus, 2 units to the left to get the directrix, and it is a vertical line as we see. Now, model that vertical line for me. Now, just be careful. I've seen so many students over the years also write it as like a point, as an ordered pair. Obviously, guys, that's not a point. That's a line. And so how do we go ahead and model that line? Well, as I already alluded to, all of the x values are the same right there. They're all -2. And if you pick any point on this line, the x value is -2. And so there is our equation. Nice. Now what I'd like to do is go ahead and draw in the parabola, but I want to be a little more specific with this. Let's go ahead and try to find a way to kind of take care of this piece. So letter E on your paper, everyone, it says, plug in 2 for x and find the y values. So I'm going to go ahead and pick a particular x. In this case, I just said 2, and there's actually a reason for me doing this, but give it a moment if you would. And I'm going to put 2 in for x, and I'm going to see what happens when we get the y value. And so I get y squared equals 8 times 2, which is 16. And I'm going to undo that square right here, so square root both sides. And I'm hoping you would agree. Let's get that equals there. Hold on just one sec. So I hope you would agree that when we undo that square, we are supposed to take the plus or minus there. And so in reality, what we have is when that 2 went in, I have a +4, but I also got a -4 out of it. And here's what's kind of interesting, in just trying to make a connection for you to some things we've talked about before. Do you remember how functions work? When an x goes in, remember, one x can only produce one y. In this case, this x goes in, and how many y's did it produce? Well, it produced 2 different values. It produced the 4 and the -4. So the way functions work, is this equivalent to that piece? Is this consistent with it being a function? And no. So an x can't produce 2 or more values here, and that's the case. So that's why this is not a function. This is why it doesn't pass the vertical line test, etc., etc. Well, regardless, let's get this moving here. So 2, 4, that would be up here. How about 2, -4? That would be down here. And then I really have an idea of what this parabola looks like. So let's go ahead and apply it. Got that. Got that. And that's a pretty good looking one right there. Humor me just one second here, if you would, with a little of the geometry. Pick any point on your parabola, your call, wherever you'd like. I'm just going to pick a point right here. and please draw right to the focus. You would measure that particular distance from our point to the focus. You would also go right to the directrix like that, coming in perpendicular. And if we drew our parabola perfectly, and I did a pretty decent job there, I'm hoping you did the same, what would we notice about those two lengths of segments? They'd be the same. And can I do that for the infinite number of points on this parabola? Absolutely. So even though the focus and directrix is not on the parabola, it's their position that basically generates the shape of the parabola. Cool. All right, not too bad, right? Can handle this. Let's do a quick investigation to back that piece up and go from there. So it says, for example 1, draw a line from 2, 4, and 2, -4. What is the length of that line segment? All right. So you know what? Let me do just a touch of erasing here because I don't want it to get in the way of what I'm looking for. Okay. Good. All right. So it says draw those 2 points that I came up with weren't totally arbitrary. So what I'm asking you to do here is connect them, of course, from one to the other. And do you see what point it actually went right through? In fact, right smack in the middle there. Do you see it went right through our focus? So take a look at this segment that I drew from this point to this point. It went through the focus, and the focus is right in the middle, of course, and it's also parallel to the directrix. Kind of see that piece? Everyone all right with that? Well, that particular segment has a line to it, or has a name to it, excuse me. I was kind of reading this piece for a sec, which we'll get to momentarily. But there's a question on here I guess we need to answer. And it says, what is the length of that line segment? Well, guys, what if I asked you to count from this point to this point? How many units is that? 1, 2, 3, 4, 5, 6, 7, 8. 8 units. And it says, is that number equivalent to the absolute value of 4p? Remember that right out here? And do you see? It's the same. So the answer is yes. And so that particular segment has a name, and you could see its connection a little bit to the model that we had here, and how kind of nice that is geometrically, going through the focus and parallel to the directrix. So let's just write what we have here, and it's going to allow us to just sketch a little easier. I'll ask you to kind of use it to help you sketch, and it'll be a quick one. So the line segment with endpoints on the parabola through the focus and parallel to the directrix, little Latin here, is what's called the latus rectum, which in English translates to, if I remember correctly here, straight side. Kind of random, but that's what we'll use, the latus rectum. All right, awesome. Hey, let's go try one more here. I think we can be a little quicker on this piece and then just do these last two in a hurry. So here we go. Let's try it out. I think example 2 puts it all together for us. So if you want to pause and do some things on your own here, totally recommended. But if you need a little more of a guide, hey, no worries at all. Let's do it. So use the equation, x squared equals -12y. So parabola on the coordinate plane, vertex at the origin, looking great. The question is, of course, which direction is this going to open? Is it up? Is it down? Is it left? Is it right? Well, again, I told you I focus just on this side of the equation, and I see that this is negative, and it's next to a y, and when I hear y, I think vertical. So negative, vertical, it's got to be opening down. So in fact, let's go ahead and put that down here. It's opening down. So here is our vertex, as I said, right at the origin, and our parabola is going to open down from there in some way, shape, or form. Okay, what is the value of p? Let's go get that piece. So remember that number out in front is a factor of 4 greater than p. We do need that p value. And again, kept the number easy for you as a multiple of 4, hoping you agree that p is -3. And so when you think about that p value, you're immediately really just thinking vertex to focus. So if p is -3, then I'm going down 3 in this case. And so let's go ahead and put it 1, 2, 3. Put your focus right here if you would, please. Excellent. And so we have that. Look how easy that is. went down 3 from my vertex, and it looks like I'm down at 0, -3 as a result. Perfect. Directrix, let's go ahead and put that piece in. Again, by definition, P is from vertex to focus, but also can be used going vertex to directrix, just the other way. So I went 3 down, of course, like I was supposed to go to the focus. Let's go 3 up. 1, 2, 3, and let's put our directrix in. So again, go perpendicular to the way you're counting there. So I was kind of going up 3, so now I want to go horizontal with my directrix, and that looks great. So my directrix will be, at some point in time here, a horizontal line. Looks like y equals, and all the values there are going to be 3. Not too bad at all, huh? I like it. Let's go ahead and do the last piece. Now, rather than plugging points into the equation to really get a good feel for this, we're going to use this lattice rectum idea to go ahead and get that width. So letter E, guys, I'm going to go ahead and put a little asterisk on my board there and ask you to do this piece. So it says, use the lattice rectum to help sketch the parabola. So here's what I'm going to write. I'll find it right in here, I guess. The lattice rectum is 12 units. Okay, so it's equal to this number right here, really the absolute value of that number, as I wrote on your sheet. And so the premise is that it's going to be a line parallel to the directrix. It's going to be a segment going through the focus, and that focus is going to be right in the middle. So if this lattice rectum is 12 units long, what that basically means, it's 12 units long with this in the middle. So I'm hoping you would agree that it's basically going to be 6 units that way and 6 units that way to get me to 12. Is that a good explanation? Is that all right? So to make it 12 units, I'm going to go 6 this way. 1, 2, 3, 4, 5, 6. Put a point. And again, I went parallel to the directrix. And then from the focus, I'm going to go another 1, 2, 3, 4, 5, and 6. Put another point. And there you go. That's how I am quickly able to get the width there. Now, let's see if I can draw it decently. Not too great. Been better, been worse. Whatever. Okay. Hey guys, if you would, pick a point and go to the focus. From that same point, go to the directrix. Now again, I can't draw to save my life, but does that look pretty good? I mean, in terms of equidistant, does that look like those are the same? Throw a couple tick marks on them? Yeah. Could I do that anywhere on my parabola? And if I drew it good enough, would that be the case? You bet. All right, I hope it's clicking. How about one more, and then we'll wrap it up. Example 3. Find the equation of the parabola with a focus at -6, 0, directrix of x equals 6. This is perfect. Be visual, though. I've been saying that all along. So here's the focus at -6, 0. Here is the directrix at x equals 6. Vertex, of course, is going to be right in the middle there at the origin. So based on this and this alone, can you tell me a few things before we write the equation? Can you tell me, does the parabola open to the left? Does it open to the right? Is it up or is it down? And in this case, vertex, go to the focus. So it's got to go left. So something like this, I'm not going to dare to sketch it, but you can kind of see it, at least a highlight of it. All right, so it's going to the left, which means a couple things. If it's going to the left, as I look to the right side of the equation, left, think horizontal, I know that I'm going to have an x on this side of the equation. That's going to be the linear term. What is p, everybody? Well, p is the distance from the vertex to that focus, and because I'm going to the left there, let's call it -6. Hopefully you see that piece on the screen. That's a -6 right there. So from here to here, 6 units left, so -6, which means, of course, our number in the equation is a factor of 4 greater than that, so it should be 4 times -6, -24. And again, I'm going horizontal, so the linear term is the x. And then we know which one's squared. It's the y that's squared. And that's perfect. That's it. That's the parabola right there. We've never really seen a parabola opening left or right before. And we've never really seen an equation where the y was squared. It's always been x squared. So hopefully this matches your idea of this over here. All right, that's great. So good introduction here to the geometry and the algebra of a parabola. Just let me know if I can help with some of the initial problems. We'll pick it up with some more algebra and more applications as we go through. Thanks for listening, of course.